Hey folks, my name is Dima. I'm a senior web developer based in Berlin. I've got more than 8 years of experience across different companies. I've been through many interviews myself and conducted plenty as an interviewer too. On this channel, we talk about passing front-end interviews and advanced front-end topics in general. If you are preparing for an interview or working on your career as a web developer, you will find some really good stuff here. Today, I want to discuss front-end architecture. Front-end architecture, I believe, a very overlooked topic. Not many of us take it seriously when we are working on projects. But here's the thing, front-end apps have become complex enough that we really need to consider their architecture as a crucial part of the development process. In this video, we will look at some popular front-end patterns, discuss their advantages, and talk about when we should use them and when we shouldn't. Let's dive in.
Now, when developers hear the word architecture, a lot of them immediately think about files and directories, and while that's part of it, it's not the main idea. Architecture isn't just about how your files is structured, it's about how different layers of your app interact with each other. You might have heard of MVC or Model-View controller, which was a pretty common pattern back in the day. Even though it's not as widely used now, especially in modern front-end apps, the concept still helps us understand how different parts of an application communicate. And here's the thing, your architecture can dictate how your files are structured, but it doesn't have to. For example, if you put every single file into one folder, which of course nobody in your team will like, you'll still have an architecture as long as your components interact in a structured way. So why do we need architecture? First, flexibility. It allows different parts of the app to be modified or replaced without affecting everything else. Realistically, how often do you replace React with Vue or Vue with Svelte? Probably not too often, but flexibility isn't just about swapping frameworks, it's about having clear boundaries between components to make maintenance application easier. Testability. Individual layers are easier to test. And scalability. As an app grows, clear separation of concerns helps manage complexity. The importance of architecture depends on 3 key factors. Project size. Bigger apps require more structure to stay maintainable. Team size. The more people working on the project, the more critical architecture becomes. Even if you're just a 2-3 person team, having some architecture is still beneficial. But in a team of 10 to 15 developers, good architecture is the must. Project lifetime. For short-lived MVP, we can prioritize speed over structure, but long-term projects need solid architecture to prevent technical debt. One thing to note, architecture often slows down initial development, but in the long run, it makes scaling and feature development much faster. Okay, now let's get into MVC or Model-View controller, the first pattern that we will look at.
Hey again, sorry for the quick interruption. We will continue in just a minute. I've noticed that almost half of you aren't subscribed to the channel yet. I would really appreciate if you could hit that subscribe button, and here are 3 good reasons why. I make videos rarely but consistently, so if you subscribe, you won't miss any new content. There are no shorts or daily uploads here, so you definitely won't get spammed. Based on what I see in the comments, this is one of the best channels on YouTube for advanced front-end developers. That's not my opinion, that's what I see in the comments. So subscribing would be a pretty smart move. And finally, as you can see, there is no advertising, no paid content, nothing like that. I don't earn anything from this. So subscriber count is honestly one of the main ways I can tell if I should keep making these videos. That's it. Thank you for listening, and let's get back to the video.
Most of you have probably heard of it, it's been around for over 36 years, and while it's not commonly used in modern front-end applications, it still contains some fundamental concepts and can be useful in its own right and can help us to understand more complex patterns. MVC breaks an app into 3 main layers. Model represents the application data and business logic. This layer is usually represented by backend, database, and sometimes API. View, responsible for displaying data. This is the UI, what the user actually sees on the screen. Also, it can include UI logic like opening a modal window. And controller acts as a bridge between model and view. It handles user input, updates the model, and tells the view what to display. Let's walk through an example of MVC workflow. Step 1. User input. This is where everything starts. User clicks a button, types something, scroll, swipe, basically any kind of interaction. Step 2. View captures the input and passes it to the controller. At this stage, the view itself doesn't process the event, it just forwards it to the controller. Step 3. Controller processes the input and interacts with the model. The controller takes the input and decides what to do with it. If the action requires updating the database, the controller sends a request to the model. For example, if the user clicks delete item, the controller tells the model to remove it from the database. Step 4. Model updates the data. The model, which is usually the backend or a state management system, processes the request and modifies the data accordingly. In our delete example, it removes the entity from the database. Step 5. Here's where things get interesting. Both the controller and model can update the view. The question is, how does the model communicate changes to the view? There are two common approaches. The first one is observer pattern. The view subscribes to updates from the model and reacts automatically. And flow synchronization. The view explicitly asks the model for updates when needed. And finally, user sees the updated UI. Finally, the changes are reflected in the UI and the user sees the updated state of the app. That's the core idea behind MVC. In the real world, it could look like this. A user clicks like on a post, the view captures the event and sends it to the controller. The controller updates the model, increments the like count in the database. The model sends the updated like count back to the view. The view updates the UI to show the new like count. Now here's something interesting. MVC doesn't have to involve a backend server. You can have a pure frontend MVC structure, where model is your state management system like Redux, Vuex, or Pinia. View is your React, Vue, or Svelte components. And controller, well, this part is a bit tricky. Some say we don't have a controller in modern frontend apps because the view directly updates the model. Others argue that hooks, composables, or middleware act as a controller-like layer. So depending on how you structure your app, you might have a clear controller layer or none at all. Now let's take MVC to the full stack. Here's how it works. Vue, the frontend UI built with React, Vue, Angular, or any other web framework. Controller, the API layer, handling client-server communication, and model, the backend containing business logic and the database. So in this structure, the frontend only handles UI logic and no any business logic. The API, or controller, handles communication and requests. The backend, model, processes and stores data. Now what happens when you're working on a huge app? Well, instead of having one massive MVC structure, we break it down into smaller independent MVC units. This is called Hierarchical MVC, where each feature, model, or page has its own MVC structure. For example, in a Redux store, we can split the store into multiple slices, each handling a different feature. In React or Vue, each page can have its own state, logic, and controller like utilities, hooks, and composables. So instead of one big MVC, we have multiple smaller MVCs all working together. Let's talk about the difference between thin and thick clients. This distinction defines how much processing happens on the client side versus the server side. So what is the thin client? A thin client keeps most of the processing on the server, while the client, web app, only handles the UI and user interactions. This is a common approach in traditional multi-page applications and static websites. You can think of a simple HTML website or a traditional web app that reloads every time you click a button. Every interaction goes to the server, which does all the processing and sends back an updated page. On the other hand, we have a thick client, also called fat clients. A thick client performs a lot of logic on the client side, reducing the server workload. Most interactions don't require a full page reload. Instead, they are handled instantly on the client side, sometimes even offline. So the biggest difference between these two, a thin client is heavily dependent on the server, whereas a thick client can work more independently with less reliance on the backend. Now let's see how MVC architecture changes depending on whether we're using a thin or thick client. In a classic MVC, you have a thin client and backend. The client just renders data and sends user actions to the controller. The controller API acts as a bridge between the client and backend, and the model backend handles all business logic and data processing. It's simpler and lightweight frontend. Bad thing, every interaction depends on the server, which means slower response time. The other option is thick client and backend. This combination is most often found in modern web applications. The client view does more than just displays data. It manages state, handles logic, and can even store data offline. The controller API still acts as a bridge. The backend model is lighter because the frontend takes over more responsibilities. Good part, it's faster on powerful devices. Better UX can work offline. Bad thing, heavier on the client side. This is why SPA, progressive web apps, and local-first applications rely on thick clients. It improves user experience, but it shifts more complexity to the frontend. With thick clients, we can implement MVC entirely on the client side. In traditional MVC, the server is the model. In modern frontend MVC, the model is a state management system like Redux, Vue, or Pinia. So now, instead of the server handling all business logic, we have model is a state manager, and controller includes composables, hooks, middlewares, or API calls. For example, in the React app with Redux, when a user clicks delete item, the view captures the event, the controller updates the model, Redux store, and the view re-renders automatically based on store changes. Is MVC still useful today? Yes, but it has some limitations. Good things about MVC: it's easy to understand, this pattern is clear and logical, and it's easy to develop and maintain. However, we can face with a fat controller problem. This problem occurs because views don't handle events and push them to the controller. This creates bloated controllers that do too much. The next problem is blurry boundaries between model and controller. Sometimes it's unclear what should be in the model versus what should be in the controller. Vue is also responsible for receiving updates from model, which makes it not just a pure UI layer. Views are only supposed to display UI, but in modern applications, they also handle events and observe for state changes. This complicates testing and maintenance. And the last problem, MVC was introduced in 1979 and is mainly suitable for classic web applications with just a presentation layer on the client side, not for modern complex web applications with client-side logic and client-side data storages. Let's look at the fat controller problem. Controller is supposed to be a bridge between the view and the model. This definition sounds too abstract and actually includes things like a sending request to the server, a handling API responses, synchronization with the backend, for example if we use WebSockets for real-time updates. Controller also manages client-side caching, and a bunch of other things. And that's the problem. The controller ends up doing way more than it should, becoming a massive bloated layer. I think it's happening because MVC was introduced in 1979. It never supposed to be used for complex web applications. Back then, client-side state management didn't exist. SPA weren't a thing, and a client-first application didn't exist. When we try to follow MVC strictly, we're most likely forcing modern web apps into a structure that wasn't built for them. When is MVC still be a good choice? MVC can still work for small to medium-sized web applications. Also, MVC can be a good starting point if scalability isn't a big concern. But MVC is not a good fit for SPA with complex state management, apps with heavy client-side logic, and the client-first or local-first applications, because these apps require stronger separation of concerns and better handling of local state. The next pattern is called MVP or Model View Presenter. MVP evolved from MVC to better fit modern web application. In MVP, the view doesn't communicate with the model directly. Instead, everything goes through the presenter. Remember how in MVC we had to put observer logic into the view? That made it too complex. MVP solved that by moving this logic into the presenter. So now the view is just a pure UI layer, nothing more. This makes the system more predictable because we have nowhere circle dependencies, easier to test because the view doesn't contain any logic, and more structured. Each layer has a clear role. Let's take a look at the difference between these two in the picture. In MVC, the view always observes the data update. We have to add observer logic to the view layer, which makes it more complex and hard to test. In MVP, the view layer receives data updates from the presenter and remains a pure UI layer. There are actually two types of MVP. Supervising controller, which is more likely like MVC, and supervising controller, the view, still handles some simple updates on its own. Only complex logic goes through the presenter. That's what I meant when I said that the view could contain some logic. And a passive view MVP. In that case, the view is completely passive. All logic is handled by the presenter. Good things about passive view are less boilerplate, less delegation code since the view handles some tasks directly, and faster development because it reduces unnecessary directions. However, view becomes harder to test and maintain. Since the view contains more logic, unit testing and development become harder. This approach is suitable for cases of simple UI, where view logic is minimal. And another option is passive view. Good thing about it, we have more clear boundaries between view, presenter, and model. The view is purely passive and the presenter contains all the logic, making all parts easier to test. Downsides: requires more code to handle basic UI tasks and can lead to overhead in cases where a simple view-model interaction would be enough. This pattern is suitable for applications with complex UI logic or when testability and long-term scalability are key concerns. Next, let's talk about pros and cons of MVP itself. The first benefit is better separation of concerns. View is purely UI, presenter handles logic. Also, it is usually more testable because view doesn't need to observe data updates. However, we still can face with the fat presenter problem. Just like the fat controller in MVC, the presenter can become a god layer if not organized properly. MVP is also not a very expressive pattern. It doesn't define where to handle backend sync, client-side caching, and other things that are not rare in modern web applications. Use cases for MVP are the same as for MVC, but MVP also suitable for applications with more complex client-side logic because it provides better layer separation and testability. The next pattern is called MVVM or Model-View-ViewModel. The main idea of MVVM is to separate view logic from business logic. And I know we have mentioned these terms before, but let's make sure we actually get what they mean. Business logic is when we actually modify data in some way. For example, if we change a username, that's type of business logic. Make a payment, that's business logic. If we remove an item from a cart, that's business logic. Basically, if it affects the application's real data, it's business logic. Now compare that to view logic. View logic is purely UI-related stuff. It's just about what the user sees, but it doesn't modify real data. For example, opening or closing a model window, disabling a button when something's loading, updating a progress bar while downloading a file. It's all about what happens visually, but it doesn't change the core data. But why does these matter? Well, when MVC and MVP were created, websites were simple HTML, CSS, and a little of JavaScript. But now, modern web applications are insanely complex. Think about something like Figma or Google Calendar. They are super interactive, tons of UI updates happening constantly. And if we just throw all this UI logic into the view layer, like in MVC, things get messy fast. We need a better way to handle view logic. That's where MVVM comes in. Let's look at how it works. MVVM has three parts. View, the UI, same as always. View model handles all UI-related logic. And model handles business logic and actual data. The new part is the view model. The view model takes care of all the UI logic. It updates the view and interacts with the model. It makes sure that the UI stays in sync with the data. That's the key difference between MVVM and older patterns. MVVM introduces another new concept called two-way binding. You can see in the picture that view depends on view model, but the opposite is also true. This means that when we change something in view model, the changes happen in view accordingly. And when we change the view, we automatically update the model. This is how two-way binding works. Let's look at the example how Vue web framework implements this concept. Let's say we have an input field where the user types their name. Normally, we would have to manually track changes like this. The user typed the name, we update the state, the UI update to reflect the new name. But with MVVM, this happens automatically using two-way data bindings. So when the user types their name, the UI updates instantly and the data model updates automatically. If you have ever worked with Vue, you have already seen this in action. Let's look again at the key differences between MVVM and previous patterns. View model is designed to store user interface data. The problem with MVC and MVP is that they don't distinguish between business and UI data. The view is isolated from the model. Many views can share a single view model. A single view cannot have more than one view model. The view model contains all the data and behavior of the user's interface window, but without any of the controls used to display that user interface on the screen. When the view model detects changes to the view, it updates its own state with two-way data bindings. If the model needs to be updated, view model modifies the model directly. Now let's look at the trade-offs of this pattern. The good parts: clear layer separation between UI logic and business logic, and scalability, easier to test, maintain, and scale. The downsides: it has a steeper learning curve. If you have never used Vue or Knockout.js, this pattern might seem confusing at first. And again, inexpressiveness. MVVM doesn't tell you where to handle things like API requests or error handling. You will still need to incorporate other patterns for that. When should you use MVVM? This pattern works best for applications with complex UI logic that needs to be tested. If you are building an app with lots of user interactions, forms with live validation, or dynamic UI updates, MVVM is a solid choice. But you probably don't need it for simple static websites. The next pattern is Hierarchical MVC. So we already discussed MVC, and one of its problems is scalability. It works great for small applications, but once your app grows, MVC starts to fall apart. What usually happens is that one controller starts handling too many things. Instead of just dealing with one model, it starts interacting with multiple models. Instead of handling a simple UI update, it's now processing data from multiple APIs, services, and backend sources. And as a result, code gets messy, testing becomes a nightmare, and making changes takes forever. This is where HMVC comes in. Hierarchical Model-View Controller is just an extension of MVC that tries to fix its scalability issues. Instead of one big MVC structure controlling everything, we break it down into smaller independent MVC blocks. Each block handles a specific feature and interacts with other blocks only through controllers. So now instead of one controller talking to three models directly, each feature or model has its own self-contained MVC structure. You can think of it like this. You have a user feature, it gets its own MVC model. You have a dashboard feature, it also gets its own MVC model. And then, if these need to communicate, they only interact via their controllers. This decoupling makes our architecture modular, reusable, and scalable. If you have worked with Angular, this concept should sound familiar. Angular has feature modules, which are pretty much an implementation of HMVC in the frontend. In a large Angular app, you don't have one global MVC controlling everything. Instead, each feature, users, orders, dashboard, get its own separate modules with its own components, services, and state management. This modular approach makes the code base easier to maintain, test, and scale. Good things about HMVC are modularity. An application can be broken down into smaller modules, which encourage independent development, facilitate maintenance, improve testability, and set error boundaries. The modular nature promotes code reuse. Bad things are steeper learning curve, it's harder to understand and develop, and possible inconsistent across modules. Each model can feel like its own mini application, and different developers or teams may adopt slightly different coding standards, patterns, tools, or naming conventions. When should you use HMVC? If you're building a large-scale application with multiple independent features, a system where different teams own different parts of the project, a front-end app that fetches data from multiple APIs and services, then HMVC is a great choice. If you are working on a small or medium-sized app, probably you don't need it. To sum it up, HMVC takes the traditional MVC structure and makes it scalable by splitting it into independent MVC blocks. It's great for large applications but overkill for small ones. The next pattern is MVVM-C, or Model-View-ViewModel Coordinator. I know that the name is too long probably, but stick with me, it's actually not that complicated. If you have already learned about MVVM, then you already know most of it. The only thing new here is the coordinator, and its job is to manage navigation and screen transitions. Why do we need a coordinator? Well, if you have worked with MVVM, you probably run into this issue. There is no clear place to handle navigation. Think about it. The view is just UI. It shouldn't be responsible for handling routing. The model is just raw data. It doesn't even know the UI exists. The view model could do it, but then it gets bloated with navigation logic. And that's exactly why MVVM-C was created. Instead of stuffing all the navigation logic into the view model, we move it into a separate entity, the coordinator. Now, whenever you need to navigate between screens, your view model doesn't handle it anymore. Good things about it: separation of concerns. Navigation logic is completely separate from UI and business logic. And better testability. You can unit test navigation logic independently. The bad thing is increased complexity. You are adding another layer to your architecture. MVVM is suitable for applications with complex navigation scenarios like multi-step workflows, for example, e-commerce checkout flow. The next pattern offers even more structure. It is called View Interactor Presenter Entity Router. The view is a passive view. It doesn't handle any logic, just displays UI and forwards user actions. The presenter prepares data for the view and makes sure everything is in the right format. The interactor handles business logic. It is responsible for fetching and modifying data. The entity is just raw data, no logic, just structured information. And the router, it manages screen transitions and navigation. So the view only communicates with the presenter. The presenter talks to the interactor. The interactor handles data from the entity, and the router takes care of moving between screens. In Viper, we split the logic into even more layers to keep things modular and scalable. Viper is used mostly in mobile development, but it can be applied to front-end web apps too. It adds more structure than classic MV patterns. It makes unit testing easier because each part is more independent. And it's better for large-scale applications where different teams work on different modules. Let's also take a look at how dependencies work in Viper. View is the part of the UI that changes most often, so we don't want other parts to be responsible for view. View itself is dependent on presenter. Presenter depends on interactor and router, which acts as a high-level layer here. And interactor depends on entity, and as usual model, but this time with a different name. Entity doesn't depend on anything. Another good thing about Viper, which I like, is that we can separate interactor into services and entity into modular entities if it's needed. Key features of Viper are designing application based on use case. We can build an application around use cases or services that define the app course feature. We have a place for API. In the Viper architecture, the interactor is responsible for fetching data. The Viper architecture has a place for handling navigation. It's a router. Viper offers better separation of concerns. Each component has a clear responsibility. It scales well. It is better suited for large applications or when multiple projects are working on different features. However, we usually need to write more boilerplate. We have to write a vast amount of interfaces for classes, sometimes with minimal responsibilities. Viper is better suited for complex long-term applications. For small applications, MV patterns are more suitable. Clean architecture. Some of you might already know this from the Uncle's Bob book. It's a well-known approach, but let's break it down and see how it works in front-end and full-stack applications. If you look at the diagram, you will notice it has 4 main layers: entities, the core business logic, use cases, the application logic, interface adapters, a bridge between use cases and external systems, and frameworks and drivers. Things like databases, UI frameworks, APIs, and external services. Dependencies always point inward. The inner layers don't know about the outer layers, but the outer layers depend on the inner layers. Entities are pure business logic. They don't care about UI, they don't care about databases, and they don't care about the frameworks. For example, think of a banking app. Entity doesn't care if the data is stored in MongoDB, PostgreSQL, or even local storage. It only cares about the business rules, like how transactions work or how overdrafts are handled. They orchestrate business logic but don't handle UI or external services. For example, if we have a list of bank transactions, entities might store all of them. A use case could be get the last 100 transactions. It processes the data but doesn't store it. This keeps business logic separate from how data is stored or how it's presented to users. Interface adapters layer is all about adapting data between use cases and frameworks. It ensures data is formatted correctly before it reaches the UI or database. It acts as a translator between different parts of the system. The interface adapter makes sure that data is converted properly before it reaches the UI. Framework and drivers is the outer layer, includes things like UI frameworks, React, Vue, or Angular, databases, PostgreSQL, MongoDB, or Firebase, and other external APIs. This layer is not essential to the core business logic. If we swap Vue for React, the inner layers don't care. If we move from MongoDB to PostgreSQL, the core logic stays the same. This is why clean architecture is so modular and scalable. Two principles of clean architecture. Separation by dividing the software into layers. The entity and external interface layers are mandatory. Other layers can be discarded if they are not needed. Additional layers can also be added. And the dependency rule. The rule says that outer layers depend on inner layers, but inner layers cannot depend on outer layers. Nothing inner circle can know anything at all about something in an outer circle. Let's imagine we have no backend or don't need to think about it. For example, if you are building an offline-first app that stores data in IndexedDB, the structure remains the same. Entities, local data models, use cases, data manipulation logic, adapters, bridge between UI and IndexedDB, and frameworks, Vue, React, and IndexedDB API. So instead of calling a database API, the use cases interact with IndexedDB instead. And the last example is a pure UI web app with just a view logic on the client side. In that scenario, the core logic is all UI based. Instead of database models, we have view logic at the center. The backend becomes just a framework. It doesn't define core logic. So clean architecture can even apply to UI-heavy apps where the all business logic lives on the backend. Good things about clean architecture, it's highly testable. Clean architecture allows for testing each layer individually, making it easy to identify and address errors. And database independent. The application is decoupled from the database, making it easier to make changes at the database level. UI independent. The UI framework is isolated, so making changes at the view level is easier. And the bad things. Higher barrier to entry. Depends on experienced and disciplined team to use it well. And increased complexity. Implementing clean architecture can introduce significant complexity, especially for smaller projects, due to managing multiple layers and ensuring proper separation of concerns. The next pattern is called Hexagonal Architecture. Like other patterns that clearly separate layers, Hexagonal Architecture makes distributed development easier. Teams in different locations can work on different parts of the same application independently using integration tests and mocks so that components can be tested in standalone mode. Another name for Hexagonal Architecture is ports and adapters. If we look at the diagram, we will see how Hexagonal Architecture works. We have business logic at the center, then we have input and output ports. Input ports are for the driving side, output ports are for the driven side. On the image you see a scenario how two teams, front-end and back-end teams, are working on the app. Team B is responsible for business logic and ports. We can think of this team as a backend team. They build the logic without worrying about the UI. They just define ports, entry points where other parts of the system can connect, retrieve data, or modify data. Team A is the UI team. They work on the adapters and the UI itself. They don't need to know how the backend works internally. They just know that input ports exist and use them to send and receive data. Of course, it might be one team or full stack developers team. This architecture can be applied to the web applications. On the driving side, left side, we have user events, web sockets, and server-sent events. On the driven side, right side, we have the user interface, client storage, and local storage. So the driving side controls the application, whereas the driven side is controlled by the application logic. Like other patterns with a clear separation between layers, the hexagonal architecture facilitates distributed development. Teams in different locations can build a single application using integration tests and mocks so that components can be tested in standalone mode. Now let's talk about contracts. This is something we can add to make development even more stable and predictable. Contracts define clear separation for interactions between ports and adapters. To enforce contracts, we can use response validators like Zod, Joy, or Yub, and integration tests. So between the adapters and the ports, we place these contracts. They can be TypeScript types, graphical schemas, OpenAPI specifications, or others. How they work? For example, client sends a request to the input port. The backend validates the request body, query params, and body structure. On the client side, we also have a contract to ensure the UI always gets what it expects. This prevents unexpected API changes and ensures frontend and backend remains in sync. Using contracts helps our team work independently and then synchronize their work. And multiple interfaces. If your app interacts with REST API, GraphQL, SLI, or multiple UI, and rich web applications. If your frontend has business logic or it is a local-first app, Hexagonal Architecture can be a great fit. It's not recommended for simple apps. Overhead is unnecessary if the project is small. And small teams and projects. If your team is small or the scope is limited, Hexagonal Architecture might be too much complex without clear benefits. Now, if we compare Clean Architecture and Hexagonal Architecture, we see some key differences. Clean Architecture is newer and evolved from Hexagonal Architecture. It focuses on layer separation within a single application, separates concerns into entities, use cases, controllers, and infrastructure. Hexagonal Architecture, older, but in my opinion, still very effective. Best suited when your system involves multiple distributed parts. It focuses on interactions between services and external interfaces. So, if you have multiple interfaces, Hexagonal Architecture makes more sense. I personally like it, I think it's easier to understand, and it gives clear separation of concerns without being overly rigid. The next concept I want to describe is Screaming Architecture. This concept is not about how models interact with each other. Instead, it's about how we should structure our code and how we should name our entities. Screaming Architecture was introduced by Robert Martin. The idea behind it is that the architecture of a software system should be immediately recognizable just by looking at its top-level structure. Things like packages name, model names, and directories in the codebase. In other words, the architecture should scream the intent and purpose of the application. It should be obvious what the system does without needing to dig into the details. I added this concept here because I think Screaming Architecture is useful for understanding another concept we will discuss later. Screaming Architecture is all about emphasizing entities in our code. If you are familiar with DDD or domain-driven design, you will see some parallels. Both approaches focus on describing architecture in terms of the business model. For example, we shouldn't structure our application around technical details like React or Vue, MongoDB or PostgreSQL. Instead, we should focus on what our application actually does. So if we are building a to-do list, for example, our features should be named accordingly, like tasks or to-dos. If we have a user management system, let's call it users, not controllers or handlers. That's the main idea of Screaming Architecture. Imagine this case. You open a project, you take a quick glance at the directory structure, immediately you should know what the application does. That's what Screaming Architecture is about. It ensures that by just looking at the structure, you can tell what this project is for, what the main entities are, and how the business logic is organized. A good top-level design should tell the reader about the business, not technical details. Focus on the business domain. Structure the codebase around core business concepts and use domain-specific names for models and features. Organize by features, not layers. Each feature should contain everything it needs, logic, data handling, and UI components, and hide technical details. Things like frameworks, databases, or APIs should be abstracted away. Keep them in lower-level models, not on the top level. In a system design interview, we should primarily focus on the architecture rather than the organizations. The final organization can be changed easily at any stage of the project by changing the architecture. Once a project has grown, it's difficult, if not impossible. That's what I call tough decision, something that we cannot easily revert. We should avoid this decision if we have no enough information to make it. Of course, sometimes it's not possible. For example, architecture is a tough, hard to reverse decision. It's not just because our team is used to working with a particular architecture. It's because as the application grows, the codebase becomes massive. And that's completely normal for enterprise projects. Rewriting an entire architecture is not just difficult, it's time-consuming and often not feasible. In most cases, the only realistic way to migrate to a new architecture is to completely rebuild the application from scratch. And if you have worked on real-world projects, you probably know how rarely companies have the budget for such a massive rewrite. This is why when you start working at a company, you might realize that the architecture is outdated and ask yourself, why does this huge company still use such an old, abandoned architecture? And the answer is usually simple. It's just too hard to rewrite everything from scratch. At the same time, choosing the perfect architecture at the start of the project is nearly impossible, because in the beginning you don't know what the application will evolve into over time. It starts in one form and a few years later it might look completely different. And at the start it's almost impossible to predict how exactly the application will transform as it grows. However, that doesn't mean we shouldn't try and eventually, I believe, choose at least a good enough architecture. The file structures and naming conventions are the opposite of architecture decisions. They are easily changeable. If you want to rename a file or refactor the structure, it's not a big deal. We just rename files, update imports, and we're done. That's why we don't focus too much on discussing file structure, because file naming and file organizations are easy to reverse. Let's move to the next and last architecture pattern in our list, vertical slices. I would say that vertical slices are probably the most modern architectural style on this list. And at the same time, I would also say that it's one of the most widely used today. To understand what vertical slices are, let's go back to clean architecture in our minds. Remember that clean architecture follows a layered approach where each layer is a technical entity. But here's the issue. Clean architecture tells us how to separate layers, but it doesn't tell us how to organize features within those layers. This lack of internal structure can sometimes be confusing. Vertical slices solve this problem by promoting a feature-based approach where each feature is a business case. Think of vertical slices as an internal structure for your architecture layers. For example, in clean architecture, we have entities, use cases, controllers, and external interfaces. Now, instead of treating each of them as a separate layer covering the entire app, we slice the application vertically into self-contained features. Each slice contains its own entity, its own use case, its own controller, and its own external interface. Every feature is self-contained inside a slice. This makes the architecture more modular, easier to scale, and more maintainable. We can also combine vertical slices with other architecture patterns. For example, in an MVP application, we usually have 3 layers, but we don't know how to internally structure them. With vertical slices, we create one slice per feature, for example, create to-do slice, delete to-do slice, and update to-do slice. Each slice internally follows MVP architecture, but each of them remains independent. Vertical slices can give us better code organization. Each feature is self-contained, making the codebase modular and easy to manage. It's easier to work on by multiple teams. Each slice is independent, so multiple teams can work on different slices simultaneously. However, there is a potential for over-engineering. If developers try to strictly follow vertical slices everywhere, even for simple features, it can lead to unnecessary complexity and extra boilerplate code. And inconsistency between teams. Because teams work independently on slices, different teams might structure things differently. This can lead to inconsistencies across the codebase. Possible solutions are use common design guides, enforce linting and formatting rules, and rotate developers across teams. When to use vertical slices? Large-scale applications. Vertical slices architecture is particularly beneficial in large-scale applications with many distinct features. It helps keep the codebase organized by feature, making it easier for teams to work in different parts of the application independently. And cross-functional teams. In organizations where teams are cross-functional, vertical slices allow teams to take ownership of specific features from end to end. This promotes better collaboration and quicker delivery of complete features. We probably should use something else for simple applications. Overhead is unnecessary for simple full-stack applications or thin web clients. And small teams and projects. The application architectural complexity might not pay off if your team is small or the project scope is limited. The feature slice pattern was defined. I would like to share a final thoughts on front-end architecture. First of all, while we explored several patterns, we certainly didn't cover all of them. My goal was to focus on the most widely used ones, such as MVC, MVP, clean architecture. However, it is impossible to cover every pattern. There are likely hundreds of them, or even thousands, and covering them all was never my intention. I also wanted to introduce you to some less common front-end patterns. For instance, we discussed Viper, which is traditionally used in mobile development. But as I mentioned earlier, just because a pattern is primarily designed for mobile application doesn't mean we can't extract valuable ideas for front-end development. In fact, front-end developers regularly borrow useful concepts and patterns from back-end development. It is completely normal for ideas to migrate across different areas of software development. The topic of front-end architecture has been overshadowed for a long time, and I think that's wrong. Even though front-end usually doesn't have complex business logic, modern front-end applications have become extremely complex. Think about it. Local-first application, offline-first applications, highly interactive UI, state-heavy applications like Figma, Notion, or Google Docs. The front-end is no longer just rendering views. It often has managed state, caching, data persistence, and even synchronization with backend services. That's why I think front-end architecture should be more widely discussed than it's now. Another important thing, patterns are not meant to be followed rigidly. While each pattern has its own core concepts, doesn't mean we can't or shouldn't adjust them to fit our specific needs. In fact, I would argue that we must adapt them. For example, we can add more layers if necessary. We can remove unnecessary layers if they don't add value. No two web applications are completely identical. Every project differs in terms of challenges that we need to solve. That's why there is no single perfect pattern that works for every situation. Each application is unique, so we must tailor our architectural approach accordingly. Another reason why using patterns is important, because they provide a common language for developers. For instance, if I describe a system using terms like model, controller, and view, most developers will immediately understand what I mean, even if there are small differences in interpretation. That's one of the biggest advantages of using established patterns.
That's all for today. I hope you found this video useful. If you did, please don't forget to hit the like button and subscribe to the channel. See you in the next one. Bye.